All right, hello, welcome, linear algebra students. This is Mr. Margraff. Um, I will be with you again next week, but I thought that I might go over some of the things, just review some of the things that you've learned since I've been gone about vector spaces. So I did the first lesson on vector spaces. Now we're talking about some of the things that you learned with Mr. Sachs while I was gone. So the null space is something that you learned, the column space. What linear transformations are. Now, we've already talked about linear transformations, but these are transformations specifically mapping from vector spaces to vector spaces. And linear independence, which we've already talked about linear independence, but now we're talking about linear independence among vectors in a vector space, which it still is the same definition, thankfully, and what bases are. So let's go ahead and talk about these one at a time, just kind of reviewing what these are before we get started. So the first one, the null space. So we typically write null A. So null, this is a matrix. A is an M by N matrix. And null A is just all of the vectors that are mapped to the zero vector. So by A. So when we'll say x in Rn, so it has to be n-dimensional vector in order to match the dimension, the number of columns of the matrix A. So it's all x in Rn such that, this is read such that, when we multiply x to A, we get the zero vector. Now this is the zero vector. This is the m-dimensional zero vector. So this zero is we'll say in Rm, the m-dimensional zero vector. Okay, so that's what the null space is. So it's important to know that the null space is always a subspace of, you have to think about it. I don't have it memorized. I just think about it every time to come up with what the subspace is. So here, notice that we're talking, this is all of the vectors in Rn, so this must be a subspace of Rn. Every time the null space of a matrix, of an m by n matrix, is a subspace of Rn. Okay. Cool, so that's the null space of a matrix. Well, what about the column space? So if we so we'll say let A equal, let me list the columns here, A1, whoops, let's use dots there. So A1 through AN. So it has n columns, just about like before, so A is m by n. And we want to talk about column space of A. So what is the column space of A? The column space is just the span. So it's all possible linear combinations. That's what the span means, is all possible linear combinations of A1 through AN. Okay, so you just take every possible combination of adding A1 through AN together, you get what's called the column space. And it's important to remember that the column space is a subspace. Remember, this less than or equal means subspace of, now you have a choice here. It's either Rn or Rm. So which one's it going to be? Well, notice that the number of rows of the matrix A is m. So this is the number of rows. So that means that each one of these elements has, so we'll say A1 through AN has we'll say, m elements. Okay, so if it has, each one of them have m elements, then that means that each one of these vectors is from Rm. Okay. Well, what about linear transformations between vector spaces? So that was column space, but now what about linear transformations? So let's see here. We'll say, how do we want to say this? We'll let V and W be vector spaces. And T, a linear transformation from v to w. So now this is if, so we'll say if. Two things have to be true. So remember linear transformations before between two sets of vectors that we were talking about before would be, or two vector spaces, is they had to have what we called additivity. So that's the first part, additivity. And then the second part is homogeneity. Homogeneity. So what is additivity? Well, remember, that means if you take t of u plus v, so I need to say u and v come from the original vector space v, is equal to t of u plus t of v. So the linear transformation can be distributed over addition. It's important to remember this is addition right here, addition in v, and this is addition not in v anymore, but addition in w. So we have two different types of addition happening here. This is the standard addition that we would know in v, and this is the standard addition in w. Now, if these are just real vector spaces, then they're the same addition. But they could be kind of abstract vector spaces where we might not be talking about real vectors. We might be talking about u and v, maybe they're polynomials or something like that. We're talking about polynomial addition there instead of talking about real vector addition like we did in multi. Okay, well, what about homogeneity? That's the scaling. So t, we'll say some constant c times u is just ct of u. Okay. So that's the same linear transformation that we understood before. So nothing new there, just underneath the guise of vector spaces. Okay. You probably talked about a special subspace that comes out of a linear transformation, and that subspace is called, sometimes it's called the null space, but other times it's called the kernel. The kernel, is it EL? I think it's EL. I just have written on my paper kern, K-E-R-N. So kernel, I think it's EL. Kernel of T is really just, I'll write it like this, the kernel of T is equal to what? So it's a set of things, it's a set of all things in V, so I'm going to say vectors in V, such that when t maps to, when t takes v, it maps it to the zero vector. Now, this is the zero vector here in W. So remember, t goes from the vector space V to the vector space W. And so this is the zero vector in W, but this is in the V is in the vector space V. Okay, so now this is the kernel, all the things that map to the zero vector of W. And this is always a subspace of what? Let's see. So let's think about it. What is inside of this set here? So we have objects in V. So this must be a subspace of V, always. So if you have a mapping that goes from V to W, then you already know at least one subspace of V, and that's the kernel of that transformation. Yeah, so that's the kernel. Sometimes it's just called null, null T, just like that. I've seen both. I've seen it written both ways. Okay, well, one more thing. What did we learn? We learned also, if you look back up here, bases. So a basis, what is a basis? So let's get that down. So first we need, so we'll say if H is a subspace of some other space, so say V, and we have a set of vectors, B, we'll call them B1, all the way through Bn. So there's my set of vectors B. And this, let's say that these vectors in B come from the space V. Okay, so these are vectors in V, but so that it's a special set, we'll say is called a basis, is called a basis, D-A-S-I-S, basis for H if two things are true. So what are they? Here's the first thing. The first thing, in order to be a basis, is the vectors b1 through bn must be linearly independent. So b1 through bn must be linearly independent. Did I talk? We've talked about linear independence, but I didn't talk about linear independence among a vector space. But it's the same principle as linear independence as we were talking about before. I'll remind you of that right after this. Okay, so b1 through bn are, we want to say, linearly independent. Okay. Okay, well, what about the second thing? So in order to be a basis, you have to have two things. The vectors b1 through bn must be linearly independent. And the second thing is that b1 through bn must span the subspace H. Okay, so in order to be a basis for H, you have to span that space. So we'll say H is equal to the span of b1 through bn. So that means H is all possible linear combinations of B1 and through Bn. Okay, well, let's talk about what does it mean to be linearly independent? So I used linear independence up there, but what does that even mean? So it's similar to what we were talking about before. We need a set, so we'll take a set V1 through Vn, so n vectors, and we'll say is linearly independent if. Okay, so what? If what? If, remember the dependence relation, C1v1 plus C2v2 all the way through Cnvn is equal to 0. This is the 0 vector. So this is called the dependence relation, dependence, or it's a dependence relation if you can find non-trivial weights. So maybe I'll call it, for now, we'll just call it the independence relation. So independence relation. Okay, so let's see. So if that is true, only when what? So only when the weights C1 through Cn are all 0. And we know this as the trivial weights. So C1 through Cn are the weights that weight each of the vectors v1 through vn. And if all of those weights are 0, if that's the only solution that makes the dependence relation true, then that means the vectors are linearly independent. So linearly independent only if we have what we have learned to call the trivial solution. Okay, good. All right, well, I think we're ready to talk about the next section. So this is all of the review. It's kind of some things that you've been learning since I've been gone. But let's talk about this next section. So this is kind of, this is moving on into using bases. So we've learned what a basis is. We just talked about that. And now what we want to do with a basis is create a new coordinate system. So we've been using kind of just instinctively a coordinate system, even all the way through multivariable calculus. We were using just a regular standard vector coordinate system that we almost took for granted. We had our axes x, y, x, y, and z. I've got my positions wrong here. So z, x, y, and z. So we almost just kind of choose our directions naturally. But what if our directions aren't so natural? What if we choose a different coordinate system? And we actually did. We chose a spherical coordinate system and a cylindrical coordinate system. But here we're going to talk specifically about coordinate systems in terms of bases. So let's look at the first theorem here and see what it says. So this is called the uniqueness representation theorem. And if you have a basis B, so we have vectors b1 through bn for some vector space V, then for every single x in the vector space, you can find weights or scalars c1 through cn that if you weight those basis vectors b1 through bn, you actually get the vector x. So that means every single x in the vector space has a unique representation in terms of these basis vectors b1 through bn. So that's why we call this unique representation. So every single vector has its own b coordinates, basis coordinates. Okay. That leads us to the next definition here. It says, suppose that you have a basis here, same basis, b1 through bn. It's a basis for v, and x is some vector in v. Then the coordinates of x relative to that basis b, sometimes we just call that the b coordinates of x, are the weights c1 through cn such that this is true, so just like we have in the unique representation theorem. So how do we write this? Notice here we put a little subscript b below x, representing that we're saying to our reader, hey, these are really b coordinates of this vector x. So this means c1 is the weight, I'm going to say the weight that we use on b1. So each one of these vectors are weighted. Here's the weight that we use on bn. So each one of those scalars represent the weight on that basis vector. So now this is not the standard coordinate system that we're used to seeing. It's a little different. There's a standard mapping. You could even call it T, that maps a vector x from x to its b coordinates, and we call this the mapping determined by the basis b. So the mapping determined by b. It's kind of a standard mapping, and it's used fairly often. Remember, this bar in front of the arrow means that we're defining the transformation. Okay. All right. I think we have enough to maybe start on the first couple examples. Before we do the first couple examples, let's just look at this note here and see what it says. It says the vector equation x is written here. So this is just the b coordinates of x for the basis b is equivalent to saying what? So we have p sub b here of the b coordinates of x. So what is p sub b? So this is the matrix B with just, or the matrix P with just columns as basis vectors. So if you take all of those basis vectors and slap them in as columns in some matrix, then that gives you the P sub B matrix. And what this does is it changes the coordinate system. It changes the coordinates of the vector, the b coordinates vector, that's x sub b here, back into standard coordinates. So the standard basis for Rn is what we're used to, 1 in the first position, 1 in the second position. So we have a bunch of, these are the standard basis. So the standard basis for R3, for example, would just be 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is the standard basis for R3. Okay. All right. I think we have enough to go look at our first couple examples. So let's go ahead and go to example 1. They give us a basis here. They say consider the basis b1, b2 for R2. So b1 and b2 must be vectors from R2. So here they are. They give them to us. Here's b1 and here's b2. Now they say, now notice that they're linearly independent. So in order to be a basis, they have to be linearly independent. So b2 is not a linear combination of b1. Okay, so it's not a multiple of the other vector is another way to say it. Okay, well, let's read what they want. They say, suppose x is in R2 as well, and has the b coordinate vector here is -2, 3. They want me to find the standard coordinates for x. So maybe it would have been good for me to write in here, find the standard coordinates. So find the standard coordinates for x. Okay, well, they told me that that x is x in terms of the basis b is -2, 3. Well, what that means is the vector x is really just, this is the weight on b1. So I'm going to say the weight on b1, and this is the weight on the second basis vector, b2. So that means x is really -2b1 plus 3b2. Okay, well, let's write out what that means. So we have -2. Here's b1. And here is 3b2. There we go. And let's see if we can multiply that out. -2, and this one's going to be 3, 6. Add those together, we're going to have 1, 6. Okay, so this is x. We're looking at the vector x right here in standard coordinates. It was almost like it was in disguise over here. So this is the b coordinates. B coordinates for x. So it's like it's in disguise. It doesn't look like what x really looks like. It's telling me like what the weights of the basis vectors are. But this is truly what x should look like. X looks like 1, 6 is really what it looks like. Okay. Well, let's look at the next example. So they say the entries in vector x are really just 1, 6, like what we just found. Are the coordinates of x relative to the standard basis e1 and e2 since? So they say that these are the coordinates of the standard coordinates. Since what? Okay, well, what are e1 and e2? We probably should be reminded of what the standard basis is. So e1 is equal to 1, 0, and e2 is 0, 1. Just like that. And so that means that if I write x as 1, 6, then this is the same thing as taking 1 of e1. Let's just write e1 here. 1 e1 plus 6 e2. So this is just going to be 1, 0 plus 6, 0, 1. So notice that this is just linear. It's a linear combination of the standard basis vectors for R2. So these are standard basis vectors for R2. Okay. And so we're still using, these vectors are still representative of, it's almost like the standard basis coordinates, but we've been using them instinctively, even way back in multivariable calculus. We didn't know what that we were using a standard basis, at least in the terms of the language that we're using now, but it was something that made sense to us while we were using them. And so now we have kind of a structure to kind of talk about what we meant by that and actually how to represent it differently in terms of other coordinate systems and other bases. Okay. Well, I think I have a graph here somewhere. Is the graph on the next page? No. Let's see if we can do a graph with this right here. I'm going to squeeze it in right here. So this is the E1 axis, and this is the E2 axis. Remember, like E1 goes up 1, just like that, and E2 goes over like this. Let's actually change the scale a little bit. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So E1 goes in this direction, and E2 goes in this direction. You could view them as like I and j from multi. Remember when we used I, j, and k for the unit directions? E1 and E2 represent the same thing here. Okay, well, now let's talk about B1 and B2. So B1 is this vector, B1. Remember, B1 is just the vector 1, 0. But what was B2? Well, B2, let's look back at the previous example. B2 was this vector 1, 2 right here. So let's write that. So that means 1 unit in to the right and up 2 units, just like this. So here's B2. Now, let's actually create another axis here, and we'll call it the B2 axis, going in this direction. So this is the B2 axis. So what were the b coordinates of the vector x from the previous problem? Well, the b coordinates, remember, they said, this is the b coordinates, were negative 2, 3. Okay. So let's see if we can make sense of that here. So the regular coordinates for x, the standard coordinates, are 1, 6. So we want to go 1 to the right and up 6. So right here. So this is x. But let's find the x in terms of the b coordinates. So this is 1b2. Let's go up to the right one, up 2. This is 2b2, so 1, 2. So that's 2b2s. Let's go right one, up 2 again. This is 3b2s. And let's see, how much do I need to go in terms of x or b1? So b1, this doesn't seem to be what I was expecting because they have negative 2 here. Let me fix. Okay, so remember the b2 coordinates here, or the x coordinates, the b coordinates for x. This is negative 2 b1, so negative 2 b1. So if we go down here to the b1 axis and go back 2, notice that when we draw a line down here, this is the amount of b2 that we need. So we have negative, let's see if I can write this in red, we have negative 2 b1, and then this vector right here is 3 b2s. We can see that here on our scale here, 3 total b2s. So that sum gives us, the vector sum between those two gives us the vector x. But we have new coordinates for that vector x. I think this picture kind of helps understand a little bit more of what bases, the coordinates for new basis systems are really telling us. It's almost like a parallelogram coordinate system. It's kind of a strange way to think about it. Okay, well, let's look at the next example here. Example 3, we have two basis vectors, b1 and b2 again. These are different. And they gave me a vector x, 4, 5. Now this is the standard coordinates for the vector x, and we can see that because there's no bracket with a lower b there. So these are standard coordinates for x. Now they actually want me to find the b coordinates for x in terms of the basis vectors b1 and b2. Now this is something that we've been doing since the very beginning of linear algebra. It was something where we would say, is this in the span? Is the vector x in the span of b1 and b2? And typically what we would do is we would say, well, c1 b1 plus c2 b2 must equal the vector x. Okay, so we're looking for multiples of b1 and b2 that gives me the vector x. Well, we wrote this as the matrix b1, b2 times the vector c1, c2, these are columns, is equal to the vector x, which we can write that as 4, 5. And then we would augment. So this is 4, 5. And then we would augment. So let's write b1 is really 2, 1. b2 is negative 1, 1. And we're augmenting that with 4, 5. And we would row reduce. So this should tell me what the coefficients c1 and c2 are that are going to give me the vector x. Okay, well, let's start row reducing. Let's see. I might do a row interchange. That's kind of a pain. Or you can just subtract row 2 from row 1. Let's just do that instead. So I subtracted row 2 from row 1, and row 2 is going to remain unchanged. Now we can subtract row 1 from row 2. Let's do that in the next line. Okay, so that's going to be 1, -2, -1, and 0 here, and that's going to be adding 2 onto the 1, so that's going to be 3 there. And then this is going to be adding 1 onto the 5, so that'll be 6. And let's continue row reducing. I'm going to divide the second row by 3, so that's going to give me 1 and 2. Okay, and then we'll add 2 to row 1 to give us the coefficients here. So that's going to be adding 4, so 3, 2, just like that. And so we can now say this is the C1 column, C1, C2. So we can read off the answer here on the end. So we can say the B coordinates of X. So B coordinates of X, really going to be C1 and C2, the coefficients, these two coefficients that we have from the beginning. And we just found those coefficients to be 3 and 2. Let's check our answer just to be sure. So we want to check. Okay. Okay, so what do we want to do? Let's take 3 of B1. What was B1? Did they tell me? 1, 2, 1. And let's see, what is, so we want 2 of B2. So this is B1. We want 2 of B2. What is B2? It's -1, 1. So this is going to be 6, 3 plus -2, 2. That's going to be 4, 5. Yeah, that's X right there. Right? So it's a way of kind of checking that you found the proper coordinates. So this is the standard coordinates for the vector X, and these are the B coordinates for the vector X. So 2 different representations for the same vector. All right, cool. I think there is, before we do the next one, I think we have to do a proof here. So yeah, use coordinate vectors to verify the polynomial. So we'll come back to this one. Let's go back and do this proof. I think we have a proof. Yeah, right here. Theorem 442. We'll do this proof here. I might have to go to the next page. You might have to write smallly to fit it all in there. But let's go ahead and do that one. I'll pull it to the next page. Okay, there we go. So how do we start here? Let's read it and see what it says. Let B be a basis for a vector space V. So that means that B1 through Bn, if you span B1 through Bn, you get all of the vector space V, every single vector you could possibly want in V. Then the coordinate mapping from any vector x in V, this is in V, goes to the B coordinates of the vector x, which is just in Rn. We have n vectors here, so Rn is a 1-to-1 linear transformation from V to Rn. Okay, so we have to show a few things here. We have to show 1-to-1. We have to show that it's a linear transformation, and we have to show onto. So they say onto. So we have a lot to show. Let's start by showing that it's a linear transformation. So our proof, the first thing I'm going to write here is linear. And remember, there are 2 things that you have to show in order for something to be linear. But before I get hot and heavy into the linear proof here, let's set up some details here. So let's set up T. I'm going to let T, I'm just going to say let T be the transformation that goes from V to Rn. And we'll say defined by, let's see, T of X equals the B coordinates of X. There we go. So we're used to seeing a transformation in terms of T like that. So I'm kind of putting that structure there so to kind of help us, and hopefully it's familiar to you when I write T of a vector X. And it's mapping. This is just a real vector in Rn, just like that. So, all right. Well, so the first thing that we have to show in linearity is additivity. So let's let two things be in the domain. So let u and v be in the domain. So these are two vectors, u and v, in the domain. And we want to show that t of uv, maybe I'll write this down. So we want to show that t of u plus v, remember, is just t of u plus t of v. That's what it means to be additive. You can distribute over addition. Okay. All right. Well, that's what we want to show. So let's see what we can do. Well, if we know that u and v are both vectors in v, then we can write them in b coordinates. So then, so we'll say, then u, I can write it as c1 v1 plus dot 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 all the way through cn vn. So, whoops, I meant to use B's there instead of V's. Let me fix that. So those should be B's. This is B1, Bn. Okay. So we have, those are the weights for U. So that means U in the B coordinates of U is really just C1 through Cn. That's a real vector. This is in Rn. Okay. Well, what about the vector v? Let's choose weights for that. So we'll choose weights this time. Let's choose d. So d1 through dn. So d1, b1 plus dot 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 dn, bn. Okay. So these are the b coordinates for the vector v. So this is going to be d1. I'm writing b's. D1 through dn. Okay, so this is also in Rn. Okay, so what about the sum of u and v? So if I write below this u plus v, like this, then that means this is going to be it's like adding like terms. We want to add the b1 coefficients together. So this is c1 plus d1 b1, all the way through cn plus dn bn. Okay, so let's see if we can show additivity here. So t of u plus v. Well, that's the same thing as t of what we just found above, c1 plus d1, b1, all the way through cn plus dn, bn. Well, what does t do? Remember what t does up here. T just maps the vector to the b coordinates. So this is really the same thing as the b coordinates. So this is c1 plus d1 all the way through cn plus dn. This is the b coordinates of the sum of the two vectors. Okay, well, then we can split this up. So this is c1 through cn plus d1 through dn. Okay, so the first one here, this is the b coordinates in terms of the b coordinates for u, and now this is the b coordinates in terms of v. All right, so we've shown additivity. This is t of u plus t of v. We've done it. Okay, now we have to show homogeneity next. Okay, now for homogeneity, let's see. So that's a constant times the vector u. So we want to take t of c times u. It might not be a good idea to use the letter c since c1 through cn is already in use. So maybe let's just say ku instead. So we'll choose constant k. K times u. So what is that going to be? Well, that means the b coordinates of ku. So let's just write that. So the b coordinates of k times u. Well, we know what the b coordinates of u are. That's right up here. So really, we want to scale each one of those. So c1, we could write it like this. So it's the b coordinates k c1 b1 all the way through k cn bn. Okay, well, and we want the b coordinates of that, which means you just rip off the coefficients. So that's going to be kc1 all the way through kcn. Okay, well, let's factor out the k. Every element has a k, so pull out that k. And now this vector c1 through cn up here is really just the b coordinates of the vector u. So that's going to be k times the b coordinates of the vector u, which, if you look, what does that mean? That's just t of u. So that's k t of u. There we go. So we have linear. So t is a linear transformation. So let's just say that. T is linear. Cool. Now what do we need to show? We have to show one-to-one and onto. So one-to-one means that if two things map to the same thing, then they must be the same thing themselves. Let me say that again. So if two things map to the same thing, let's choose two things out of the domain. So I'm going to, this is a new line of the proof, so let's forget the u and v that we used before. So I'm going to choose two things out of the domain, let u, v be in the domain. Is the domain v? Yes, v. Uh, so that something's true, but that t of u is the same thing as t of v. And then what we want to show, let me put this in parentheses, we want to show that that implies u is actually equal to v. So one-to-one means that if you choose two things in the domain and they map to each other, then they have to be the same thing themselves. Just like 2 squared is 4, and negative 2 squared is also 4. So two things that map to the same thing, but they're not the same thing. That's why x squared is not one-to-one. Okay. All right. So how do we go about showing this? Well, what this line means, t of u is t of v, then, so we'll say then the b coordinates of u have to be the b coordinates of v. They have the same b coordinates. Then that means that if u equals c1, b1 all the way through cn, bn, then u equals c1, b1, cn, bn, which is the same thing as v. They have the same b coordinates, so you take the same coefficients. So we can say, therefore, u equal v, which is what we set out to show. So t is one-to-one. All right. That might have felt almost like trickery. It's because it's almost so so simple that it feels so, it's almost like there's nothing to be said. But we try to break it down as far as we can. The fact that the b coordinates are the same tells me that they have the same coefficients, the same weighting. And if they have the same weighting, then they're the same vector, is really what it means. Therefore, t has to be one-to-one. Well, let's show onto next. So how do you show onto? So this was one-to-one, and now we want to show onto. Okay, well, onto means that if you choose something from the range, then there has to be a vector in the domain that maps to it. So choose something in the range. What is the range here? It's Rn. So let's just choose something out of Rn. Let this vector y be in the range. Okay, so then y is really y1 all the way through yn. Okay, now let's find some vector inside of the domain that maps to this. Okay, I'm going to find a vector inside the domain that maps to y, so that the b coordinates of my vector happen to be y. So let w be in v so that something is true, so that, let's say it like this, is going to be y1, b1, Again, it feels like trickery, but it's not. Yn Bn. So notice that I just chose the weights. I used y1 through yn to be the weights of our basis vectors, and then I called this vector w. This is certainly in V, because remember, V has the basis vectors b1 through bn. So w is in V, and these are the basis vectors. So then I'm going to say, so T of W is the B coordinates of W, the vector W, which is the B coordinates. So that's going to be B1, Y1 through YN. So this is Y1 through YN, which is Y. Man, so what that tells me, so this implies, we'll say therefore, or implies that T is onto. So why? Why is it onto? Well, by choosing an arbitrary vector inside the range, we chose an arbitrary vector in the range. There was nothing special about y. I just chose a random one. And then I showed that there has to be a vector w that maps to that random one. In other words, the mapping covers the entire codomain. So let me write that down. Mapping covers entire codomain. What is the codomain? The codomain is Rn. So the range is the codomain. Remember that distinction between the codomain and the range? They're not the same thing, but they are the same thing when the mapping is onto. In this case, they are the same thing, therefore the mapping is onto. Okay, well, good. I doubt you were able to fit that into that little space there. I need to maybe tweak that in my notes for next year. Let's go to the next one. Example, I think we're up to example 4. Did we do example 3? Yes, we did. Okay, so let's do example 4 next. It says use the coordinate vectors to verify that the polynomials here, we have 3 polynomials here. Let's label them. I probably should have labeled them. This is P1, P2, and P3. Show that they're linearly dependent. In other words, you can write one of them as a linear combination of the others. Okay, well, then let's say, so let's just say P1, let's write the standard coordinates for P1 in the standard basis. What is the standard basis for P2? Let's maybe write that down before I get to the B coordinates. So standard basis for P2. This is all second degree polynomials. All second degree polynomials. Okay, so what is the standard basis? We'll use an S for the standard basis, is going to be just 1 t and t squared. So if you choose each one of the polynomials, 1 t and t squared, so that's you have the constant, the linear, and the quadratic. That's enough to create all possible second-degree polynomials. If I take any linear combinations of those 3, I'm going to be able to create any polynomial. So now let's write P1 in terms of t is just 1 plus 2t squared. And let's write the standard coordinates for this. So this is a vector in terms of these basis vectors. So this is going to be 1, 0, and 2 inside the standard coordinates. Okay, well, what about P2? Let's write P2 here. That one is 4 plus t plus 5t squared. And let's see, this is going to be P2 of S. So let's see, that's going to be 4 in the constant, 1 in the linear, and 5 in the quadratic. And we have one more vector, P3. Let's see, that is 3 plus 2t. So this is P3 in the standard coordinates, which is going to be 3 in the constant, 2 in the linear, and 0 in the quadratic. Okay. All right, now that we have these in real vectors in R3, we can actually see if the real vectors are linearly independent. So by showing that these vectors are linearly independent, that's a little bit easier. That's using row reduction. We're used to doing that, but showing like how much of P3 do I need for P2, it's kind of hard to kind of come up with that on your own, but we can have an algorithmic way of doing this here. So let's slap these vectors in into a matrix here. So we're doing a linear combination of these vectors to see. So this is the first vector, P1, P2, P3, and now we're augmenting this with the 0 vector to see what the weights are. If we can find a dependence relation, then the vectors are linearly dependent. So let's start row reducing. We'll take 2 of the first row and subtract it from the last here, so that's going to be -3, -6. Okay, that means I can eliminate that second row, or the third row. So let's go ahead and eliminate that one. This is going to be 0. We have to subtract 4 of the second row from the first. So it's going to be -5. 0, 0, 1, 2, 0, 0, 0. Okay, there we go, row reduced. What does this tell me? So these are the weights, C1 through C3, of my polynomial vectors here. So that means that if I write the vectors C1, C2, C3, this is really telling me that I just need -5s, or 5C3. Let's see, I add that over to the other side, so 5C3. -2C3 and C3. This is the general solution. You could view it that way. The general solution, or the general solution for the system. And so what that tells me is I take 5 of the first polynomial, that's 1 plus 2t squared, minus 2 of the second, 4 plus t plus 5t squared, and then plus 1, that's C3, of this last one, should give me the 0 polynomial, just 0. So if I subtract these two to the other side, then 3 plus 2t is equal to 2, 4 plus t plus 5t squared, minus 5, 1 plus 2t squared. So what that tells me is that this is P3 of t is 2 I think that one is P2, yep, P2 of t minus 5 P3 of t. All right, so this is a dependence relation for the polynomials. So this right here implies polynomials are linearly dependent. Notice that we wrote P3 in terms of P1, or P2 and this is P1, P1 there. So we were treating polynomials like vectors, and then you being able to transfer between real vectors and polynomials and back and forth is a very useful skill. It's one that simplifies all sorts of problems of simplification. It's a lot easier to deal with a matrix than it is to combine like terms and like coefficients and stuff. By row reducing a matrix, we were able to find the combination of the polynomials that gave it to us, rather than, I mean, I guess you could probably, some of you are very clever, you could probably figure out that combination before before I could finish the problem, but maybe if it was a 5th degree polynomial, I could beat you or something like that. But okay, well, let's look at example 5, and I think this is our last example. Yeah, so let me make sure that I haven't left anything out in our notes portion, and then we'll do this last example here. So the notes portion, let's see here. We have a definition down at the bottom. An isomorphism. I forgot to mention that at the proof. So let's go back and look at that proof. I should have mentioned it at the end of the proof here. When you have a linear transformation that's both one-to-one and onto, that tells you that you have a special type of transformation called an isomorphism. So what exactly does that mean? Well, what that means is that these two spaces, V and Rn, are almost identical, up to a name change. If you just change the names of the things, then these two spaces, V and Rn, are exactly the same. So the fact that they have a basis, V has a basis vectors, in total basis vectors, tells me that these two spaces are isomorphic, or at least with this underneath this certain transformation, that transformation is isomorphic. Okay, which tells me it behaves, the transformation behaves the same on both spaces. Okay, let's read the definition though. Let's go look at that. It says, in general, a one-to-one linear transformation from a vector space V onto a vector space W is called an isomorphism. So now the transformation is what is an isomorphism is. We sometimes say that the spaces are isomorphic, but that comes in kind of a different topic. For now, we'll just say transformations are isomorphic, or isomorphisms, if they're one-to-one and onto in a linear transformation. Yeah, so this previous theorem is an isomorphism, this particular mapping. Okay. Now let's do that last example. Oops, passed it up. Okay, here we go. What does it say? They give me a vector v1 and v2. They're both in R3 and then a vector x. What do they say? They say B is just a set of v1 and v2. Then B is a basis for H. So H happens to be the span of v1 and v2. So I'm assuming that v1 and v2 are linearly independent. Well, if you look up there and you add them together, yeah, they look linearly independent. If I take 3 of v2 and add it to v1, it doesn't give me the 0 vector, so there's no possible way that I can get, they're not multiples of each other. So determine if x is inside the span of those two vectors. If it is, find the b coordinates of x. Okay, well, we're asking, can I take weights C1 of V1 and C2 of V2 and give me the vector x? Is it possible? If it's not, then once we start our row reduction, then we're going to have an inconsistent system. But if the system is consistent, then we will have b coordinates, and this vector x is in the span of those two. It's in a subspace. Okay. Well, let's see here. So what is the vector x? It's 3, 12, and 7. And now we can write this vector equation as a matrix equation. So let's write this as 3, 6, 2, negative 1, 0, 1 times the vector c1, c2 is 3, 12, and 7. Okay, well now you know that we can write this as an augmented matrix, and you probably could have jumped straight to this. And if you do on a test or a quiz, that's perfectly fine with me. I'm doing this right here. I'm showing this for your benefit. I want you to see where it's coming from. We're writing that equation there because we're seeing that they're a linear combination. This is what it means to be in the span of V1 and V2, is that you're a linear combination of V1 and V2. So I'm writing these two for your benefit, but if you want to jump straight down to here, that's fine. I just want you to label things clearly in your answer. Okay, well let's start row reducing this. Let's get to it. Oh man. Let's take one of the third one and subtract it from yeah, let's use the third one. I'm trying to think of the best way to row reduce this. It doesn't matter. I'm going to use the third row to eliminate the top two. So let's That's going to be 0, minus 3, and 7 minus 2, so it's minus 14 minus 2, just like that. This is 2, 1, and 7. So I'm leaving the third row unchanged, and then I'm just going to subtract 1 from the first row. So that gives me a 1 there, a negative 2, and a negative 4. Okay, now let's eliminate that last 2 there. There probably was a quicker way. I didn't see it. Eliminate that 2, that means add 4, so that's 5, and add 8, so that's 15. Now we can take a fifth of the last row, and let's see what that gives us. I'll negate that. A fifth of the last row is 1, 3. This is not going to be consistent. Did I make a mistake? I found a mistake here. Let's see. So when I subtracted 3 of row 3 from row 2, I mistakenly only subtracted 2 7s from that 12, and I should have subtracted much more than that. So that means I should have a negative 9 here, so I'm sorry if you copied that down. So this is a negative 9. Okay, so let's fix that in the next step as well. So it turns out that this is going to be, let's fix this. It looks like this will be consistent. It looked like I had it inconsistent before, but by dividing the second row by a negative 3, we're going to have 1, 3, which those 2 rows eliminate, and then we can eliminate that negative 2 above as well. So let's do that. Okay, so that negative 2, that's going to be adding 6 to that 4. It gives me a 2, 3, and 0. Okay, we've done it. So this column is the C1 column, and this is the C2 column. So what that tells me is C1 is 2, and C2 is 3. So let's say that here. So x, the b coordinates of, let's just write x first before we write the b coordinates. So x is equal to 2 v1 and a plus 3. I'm using this equation right here, bringing it down, 3 v2, and I'm using the c1 and c2 that we found right here in our row reduction. Okay, so what this tells me is the b coordinates of x. So I can now write x in terms of is the basis b, is that what we called it? Yeah, b. So now the b coordinates of x are just 2, 3. Now there's something interesting here. Notice that x is from what space? Let's look. X is from R3. But now notice the B2 coordinates of x. It's in R2. So we've lost a dimension there. We've compressed the information somehow. Well, what happened? How did that happen exactly? Well, notice that x is in a space H, and the space H is spanned by 2 unique things, v1 and v2. And so everything in H can be represented by v1 and v2. So x here is actually being represented by those 2 things, 2 of v1 and 3 of v2. And so it's the only reason that we were able to condense it and reduce that dimension is because it was in a more specific space. And so now we're talking about the b coordinates of x rather than the standard coordinates of x in terms of R3. So we've really changed the way that we're looking at it. Okay. Well, next class, I don't think, maybe I won't do a quiz just the day we come back, but next class we'll talk about everything and some of the homework that you've been doing since we've been gone. So that would be sections 4.1 through 4.4, so homework. And we'll discuss this, so we're going to discuss the homework. And then we'll probably have a quiz, not the day that you see me next. So that's a quiz on, I'll probably do 4.1 through 4.3. And that will be, what will the date be? There's a teacher work day on the 16th, and then the 17th I have a B day, and the 18th. So that will be the 18th. So on Wednesday, the 18th of April. Okay, so that's the attentive plan for now. We'll have a quiz on that day. Try to get all of the homework done, even section 4.4, because I'd like to discuss everything that we've learned. Do as much as you can. If there's a problem that you're struggling with, just move on. Do what you can. We'll talk about it when we're together. I think that's all. All right. Well, I will see you guys next week.